All right, ladies and gentlemen, we are on part 1 of the 6-3 video here. There will be 2 parts in this video, so make sure that you're paying attention to that when you go to look for your next video. We are going to be looking at examples 1 and 3 in your student companion, and I will put up the page numbers here so you know where to go. All right, so we are in Student Companion pages 124 to 126. We are looking at exponential growth and decay, which is just a way for us to use the exponential functions that we've been experimenting with in 6.2. So here we have a problem. Usually exponential growth has to deal with things like population, especially bacteria population or animal population in science, but they can also deal with money. So here we have the population of Hillville grows at an annual rate of 15%. So every year they grow 15%. What will the estimated population of Hillville be in 5 years? So in order to find this using an exponential function, okay, we're going to model this exponential growth. So again, these highlighted words are good vocabulary words for you to have. But in order to model this with a function, we're going to take that traditional, or that same exponential function equation that we saw on 6.2, and we're going to use that to model exponential growth. So we still have our A. If you remember, our A was our initial value. Our B was similar to our slope, but at a constant rate, where we're doing an exponent instead of like constantly adding, we're constantly multiplying that rate, okay? So an exponential growth function has a growth factor that is equal to 1 plus the growth rate. And you can see here that it's color-coded. So the growth factor is the same thing as my rate, okay? So this right here is similar, or we can use it to represent a growth factor. And a growth factor is 1 plus the rate. So our new function, we still have the A, but instead of timesing it by B, we're going to times it by our growth factor of 1 plus R, and we're still raising it to that power of X. So our growth factor is actually referring to both this part and B, right? So all we did was replace B with 1 plus R. Okay. So if we're going to solve this problem, we're going to go ahead and take this new function right here, our growth factor, our exponential growth function, and we're going to let X represent the time in years. A is our initial amount, just like we had done on the previous video. Our A is always our initial value or amount in this case. And R is our growth rate. So in this problem, our initial amount was 5,000. That's the population. Our rate is 15% because they're growing at 15% every year. So I'm going to write that as a decimal, 0.15. And I'm going to plug it into my equation. And then we're going to solve this, right? This is our function formula. In step 2, we're now going to solve this. Now I can solve this by using a scientific calculator. I am going to do order of operations, which says my exponents come first. So I'm going to do 1.15 to the power of 5 years, 5 first. And then I'm going to take that answer and times it by 5,000. And you'll see here is my answer. That is the same here. So it's an approximate answer because they're rounding to the nearest hundredth. Okay, but that's how you do it on a calculator. In conclusion, that means that this Hillville, whatever this place was called, in 5 years, the population is expected to be about 10,057. Again, they rounded to a whole number because you can't really have. All right, so you're going to go ahead and take a look at Valley Town and try to figure out if they can be represented, if they have exponential growth. So think back to 6.2, where you were looking at the difference between an exponential function, and a linear function. Okay, you're basically in this question right here, you're trying to figure out, is Valleytown exponential or linear? All right, I wanted to do one more example on growth, exponential growth and growth factor. This isn't in your student companion, but if you can follow along with me, you're welcome to write this down in the little gray area, or because we're not going to do example 2, you can just do this in the example 2 spot, but I wanted to give you one more example. So here we have a value of a painting that's increasing by 56% every year. If the painting was purchased 2 years ago for $10,561, how much is it worth today? So we're going to fill in the information here straight from our equation. We're using our rate is our 56%, and we have to turn that into a decimal. So that's where they get the 0.56, okay? We're going to add 1 to that. Our initial value is that 10,561. And then our exponent here is the number of years. So in 2 years, we would want to know. So that is how they got all of this right here. And when you multiply that out on your calculator, you're going to get about $25,701. So we would say that it would be worth about that much. Okay, we're going to jump on over to example 3 and now look at the other side, which is exponential decay. So obviously if things can grow exponentially, they can also decay exponentially. So here we have a video that's labeled a fan favorite as it receives at least 1,000 views per day. Amelia posts a video that gets 8,192 views on the first day, and then the number of views decrease by 25% each day. So that makes sense. As the video becomes old, it starts losing interest and losing views, and that can happen at an exponential rate. It can happen really quickly. In how many days total will the video stop being a fan favorite? Okay, and how many days basically will it have like no views, close to no views? So we are going to do the same thing that we did here, but we're going to model with exponential decay. And our equation looks very similar, but because decay is going down, we're going to subtract from 1, and we're going to take that decay factor. So before we had a growth factor, that was R. Now we're going to have a decay factor of R, and we're going to take that away from 1. Okay, so I'm going to write my equation over here in orange so that you can see the 2 equations. So my decay, exponential decay function is going to look very similar, but here I'm subtracting. This R we're going to call a decay factor. And again, you're writing this all down in your notes, whoops, so that you know what I mean when we're talking about this. Okay, there's our equation. So if I'm taking the information from here, I'm first going to model the situation where, again, letting X be the time in days, how many days go by. A is our initial amount, the initial amount of views, and R is our decay rate, how much it's going down. So because we started with 8,192 views, that's going to be A. That's still our initial over here. Okay, we are then going to subtract from 1 25%. Oops, because up here it says 25%. And then we're going to plug this into the calculator to figure it out. And it says that the decay factor is written as a decimal less than 1 because I'm reducing by 1%. So here's my equation. And then the last thing you do is just going to solve. So it says you use a graphing calculator. I can show you one here too in my scientific calculator that if I clear this, I am going to go ahead and do, taking this formula right here, if I'm looking for so the reason they're using this is because they're trying to figure out how many days. So another way that you could do this is by taking the 1,000 and dividing and then finding the exponential. But basically they made a table saying, okay, well, if my exponent, my x is 4, then what does that make? If my x is 5, what does that make? If my x is 6, right? And they just kept going, okay, to figure out when it would be not a fan favorite. So they're saying it's in 8 days. I'm assuming that because it's less than 1,000 views, that's when it stops being a fan favorite. It's kind of a silly estimation here, but you can see that it keeps going down here. But the whole point of this problem is this guy right here. Can you create this formula? Down here, they just basically made a table on a graphing calculator. Okay, your next job is to take a look. It says a video is labeled as a fan favorite. Here's the views per days. Suppose the number of views decreases 20% per day. In how many days will the views be less than 1,000? Okay, so you're going to do the same thing that they just did. We're going to scroll down a little bit over here, maybe. There we go. Just to get a little bit more room. And we're going to fill this in. So you're going to make your equation. And then when you're done making your equation, oh, because this is x, boop, boop. When you're done making your equation, you're going to make a little table and say, well, if x is 5 days, then what does that make my views? If x is 6 days, what does that make my views? And you would just plug into the calculator from your formula. Okay, so see if you can find that. All right, so since these examples are kind of short, you're going to go ahead and go to page 126 in your student companion, and I want you to go ahead and work on problems 5, 6, 7, and 8. I think it's 5 through 8. Let's check here, but basically you're just writing the exponential growth or decay function for the situation. There's no solving right now because they're not giving you like for how many days. They're not giving you that. Exponent piece, they're just having you write it. Yeah, so just up to 8. We're going to go ahead and do 5 together really quick so you kind of understand what it's expecting you to do. I'm going to just shrink this a little bit. There we go, so that I have a little bit more room to work with. So let's do this. Ooh. Okay. So I'm going to go ahead and do just the first one. We're going to write out the function. So I'm using growth. So I'm going to start here. And it says, write an exponential growth or decay function for the situation with an initial value. We know that's A of 100. So again, if this is my equation, and because it's growth, I'm going to add. So this is A times the 1 plus my rate of 5%. 5 is equivalent to 0.05 x. And that's it. That's all they want you to do is just, can you write the equation right here? So this is my answer, okay, for number 5. So can you do 6, 7, and 8?